So hi everyone, we're from group 23 and we're going to explain how to design ALU part of the Risc-V CPU. So we need to design using these specifications. So first we need to design the full adder gate level schematic, and then from the truth table we create a K map. Based on the Karnaugh map simplifications, the Boolean expression for the full adder outputs are as shown above. Then, from the previous design of full adder, it is reused as a modular building block to form a 4-bit ripple carry adder and subtractor. So the subtraction is achieved by inverting the B input using XOR gates. So in this case, the B input is connected through XOR gates, which are controlled by the signal R. So when R is equal to 0, the XOR gates pass the B input unchanged and the circuit operates as a normal adder. So when R is equal to 1, the XOR gates invert each bit of the B input, producing the 1's complement of B. So in summary, when R is equal to 0, it will go through addition, and when R is equal to 1, it will go through subtraction. And then in order to do arithmetic operations, XOR and XNOR is required to support bitwise logical operations. So the XOR operation produces a logic high output when the input bits are different. For example, a 4-bit XOR logic unit is implemented by applying the XOR operation bitwise to the input operands A and B. So each bit of A is XOR with the corresponding bit of B, producing a 4-bit output. So for the XNOR operation, it is just the complement of XOR operations, and it is produces logic high output when the input bits are identical. So the output of XOR and XNOR is going to connect it with the multiplexer. So this is the functional table of 1-bit 4x1 multiplexer. Based on the table, the Boolean expression is as shown above. So that concludes that it is built using 2 NOT gates, 4 AND gates, and 1 OR gates. By combining these symbol blocks for 4, we will produce a 4-bit 4x1 multiplexer. So the 4 bits 4x1 multiplexer is controlled by the inputs in each block. For example, the first bit of I0, which is 0, is connected to the I0 input of the first block. The second bit of I0, which is 1, is connected to the second block, and as follows. So to make a register, 4 of 1-bit D flip-flop components are combined to form a 4-bit D flip-flop, as shown at the logic circuit above. And then the ALU is constructed by integrating several key components, which is 2 blocks of multiplexer, 1 block of an adder subtractor, and 1 block of register. So the outputs from the multiplexer along with the ALU cell signal are connected to the adder subtractor block. So the clock and reset signal along with the 4-bit outputs from the adder subtractor serve as input to the register. So on each clock positive edge, the register captures the input data and outputs it as the final ALU output. So finally, the waveform result. So in the waveform result, as we can see that A0, A1, A2, A3, B0, B1, B2, B3 is a random 4-bit values. So the operation is proceed as follow, which is the first stage is by multiplexer, second stage is by adder or subtractor, and third stage is resettable register. So at the third stage, the result from the adder or subtractor are used as input for the register built using positive edge, and it is triggered the D flip-flop. So the register is equipped with an active low clear feature. So when the reset input equals to 0, the I is equal to output, it is immediately clear to 0, 0, 0, 0. So that's all from us. Bye.